Right now, massive volumes of highly sensitive encrypted internet traffic, including financial records and military communications, are being intercepted and stored by state-sponsored actors. They cannot read a single line of this data today. They are executing a strategy known as Harvest Now, Decrypt Later. Hackers are hoarding secure files on their own servers, betting that a future breakthrough will eventually crack the encryption protecting them. The tool they are waiting for is a fully functional, large-scale quantum computer. Because this hardware is steadily moving from theoretical physics to engineering reality, today's private data has a shelf life. Even if your communications are secure right now, they are vulnerable to the machines being built tomorrow. Classical computers rely on binary bits, locked as 0 or 1. Quantum computers run on the qubit. Through superposition, a qubit represents both states simultaneously. With entanglement, qubits link and instantly influence each other, navigating millions of combinations at once. This nonlinear logic allows a quantum processor to bypass the computational roadblocks that make classical cryptographic barriers effective. Most secure data transmission on the internet relies on protocols like RSA. It derives its security from the mathematical difficulty of factoring large prime numbers. For a classical computer, finding the 2 prime factors of a 2,000-bit number would take billions of years. In 1994, Peter Shor developed a theoretical framework designed specifically to find the factors of these large numbers. Shor's algorithm provides a direct computational path to bypassing the protections of modern encryption. The algorithm utilizes quantum interference to amplify correct answers and cancel out incorrect ones. This allows a quantum computer to find those hidden prime factors exponentially faster than any classical machine. Shor's algorithm proved mathematically that the foundation of our digital privacy is vulnerable to a sufficiently powerful quantum computer. This image shows a paper published by Google in 2019, announcing they had moved this threat from purely theoretical math into physical engineering. They achieved this using their Sycamore processor, a physical chip built with 53 functional superconducting qubits. The architecture relied on adjustable couplers that gave the team precise control over the interactions between neighboring qubits. This phase space diagram shows the results of their experiment. The Sycamore processor completed a highly complex random sampling task in exactly 200 seconds. Looking at the data point marked by the star on this graph, Google estimated that the same calculation would take the world's most advanced classical supercomputer 10,000 years to finish. This claim triggered an immediate industry debate. Researchers at IBM published a rebuttal arguing that Google had underestimated classical computing methods. IBM asserted that if a supercomputer had access to enough hard drive storage, it could complete the simulation in just 2.5 days. The experiment proved that quantum-accelerated computation can be executed by physical hardware, transitioning the technology from a mathematical model into a functional system. The reason encryption hasn't been broken yet is that we are currently in the NISQ era. NISQ stands for Noisy Intermediate Scale Quantum, which refers to processors that lack advanced error correction. Because qubits operate at the subatomic level, they are extremely fragile. Any slight environmental interference, a change in temperature or a stray magnetic field, causes decoherence, where the qubit loses its quantum information and the calculation fails. To fix this, engineers group unstable physical qubits together into an error-corrected logical qubit that executes operations without succumbing to noise. Running Shor's algorithm requires thousands of these logical qubits, meaning millions of physical qubits working in tandem. The scale of this engineering overhead is currently the single barrier standing between quantum computers and our private data. A global race is underway to overcome this limitation, with different teams pursuing distinct paths to hardware stability. Companies like IBM and Google rely on superconducting qubits. To keep these circuits stable, they must be suspended inside dilution refrigerators, cryogenic systems that chill the chips to fractions of a degree above absolute zero. Other teams are abandoning deep freeze environments entirely. Some use trapped ion systems, manipulating atoms with lasers, while others develop photonic processors, computing with pulses of light at room temperature. In response to this hardware progression, the cybersecurity industry is moving toward post-quantum cryptography. This is a new class of algorithms designed to be mathematically immune to both classical and quantum attacks. Governments and telecommunication firms are already running field trials over existing fiber networks to deploy these protected encryption methods for critical infrastructure. While the harvest now threat is real, the transition toward a quantum-safe infrastructure is well underway. If you want to keep up with how these emerging technologies are evolving, hit the subscribe button below.